length of a code is related to brute force. With brute force, Eve can possibly try all the keys, so it is important that we understand how many keys are actually possible for the number of bits that we use in the key. So we can see in this case that for an 8-bit key we only have 256 keys, not too difficult, and as we increase, 56 bits is one of the most significant, and the reason it's significant is that one of the most important encryption algorithms, DES, uses a 56-bit key. So in this case we have 7.2 and 16 zeros is the number of keys. And the more bits that we have in our key, the larger the key space will actually become. So with brute force, as we said before, Eve tries all the keys and eventually she finds something that looks like a message. She might have several of these and she can actually pick off which one looks most like the original message. And the key thing is that this all takes time. Obviously it's not going to be done manually because it would take Eve a long time to search through all the codes in hexadecimal or base64. So this is typically done automated with a computer program. Okay, so let's take an example. We'll take a fairly difficult key of a 64-bit key and see how long it will take Eve on average to find the key. It has 1.84 and 19 zeros, or 18.4 million different keys from there to there. Hopefully the key isn't at the start and will be somewhere near the end. So the thing is that we need to determine how long it will take by brute force to crack it. Okay, so let's say that it will, on average, it will take 0.9 times 10 to the 19 goes. And we take a fairly fast computer with a 1 gigahertz clock, so it checks 1 time every billionth of a second, or 1 nanosecond. If we do the calculations, this times this, we get that the code will be cracked with inside 9 billion seconds, or 150 million minutes, or 2.5 million hours, or 285 years. So that seems a fairly long time that we have for the message. Obviously every message has a certain time that it needs to stay secret. So in this case 285 years seems a reasonable amount of time. Okay, so let's say it takes 285 years now. One thing that we do know is that computers typically increase their performance every year. So let's say that our computer systems are doubling in performance. So this year it takes 285 years, next year it only takes 140 years. And then what we can see is that after only 17 years, we are down to 1 day. So something that took us 285 years today, in 17 years time, because of the improvement in computers, only takes 1 day. And the worrying thing for this is that DES was developed 30 years ago. So we can see that computer systems have improved greatly since then. So we can see here that we're only actually taking 20 hours to decrypt what took us 285 years. Along with this, encryption is one of the most scalable applications when it comes to parallel processing. What we can do is that we can split the key space, in this case into 2, and we can give half the keys to one computer and half the keys to the other, and that way we'll take half the time. If we had 4 computers, we would take a quarter, 16 computers will take a 16th of the time, and 256 computers will take 256 of the time. So we can see now that with one processor it might take 104,000 days, but with an array of 1,000,000 computers. So if we had a processing array, it can only take 2 hours. And then if we look at that in terms of increasing computing power, we can see that very quickly now, just within year 5, we go from thousands of days down to several hours. And to show the problems with the DES code, the Electronic Frontier Foundation decided that it would build an array of processors. In this case, we have 1800 processing elements, and they eventually cracked 56-bit DES in 2.5 days in 1998. And now, for less than $10,000, it is possible to crack the 64-bit DES with this system, the Copacabana. Encryption is obviously a challenging area, and RSA Labs have posted several challenges to the community to be cracked. So we've seen there that in 1997, 1998, DES was cracked within 2.5 days, and then DES 3 was cracked in 22.5 hours, and the 64-bit RC5 in 2002 was cracked within almost 1800 days, of which 83% of the key space was tested. Currently, a 72-bit challenge has been posted, and many people are working on this. The distributed.NET works in a way that it is possible to download a process which runs when the screensaver starts. So in this case, the screensaver is starting and stopping. So we can see here it goes up to maximum CPU utilization when the screensaver is on, and in this region it's computing some encryption keys related to the RC5 algorithm. We've stopped the screensaver here and started it back again. So it's possible to create a massively parallel processing system that can search encryption keys. Along with this, there are some exceptional computers in the world. One of the largest is the Blue Gene system, which is used by the Department of Energy, and it has 131,000 processors and is nearly 2 million times more powerful than a desktop computer. Redstorm also is a fairly powerful machine with 126,500 processors.